Umbra Software is a games middleware company based here in Helsinki, focusing on rendering optimization. We're currently 10 people, constantly looking to grow, obviously. The company's been around since 2006. Most of the engineers working for Umbra have been tackling rendering optimization issues longer than that for over 10 years now. And the various technologies developed by Umbra have shipped in some of the most influential and ambitious game releases in the past years. Here you see some of our clients that have shipped games utilizing Umbra rendering optimization. We're currently in the third generation of our Occlusion culling product. We're building Umbra 3 to target next generation game engines. We're working relatively closely with some of the key partners all over the world. Here you see some of them listed. I'm sure you're familiar with the names here. It's probably worth mentioning that these studios are known for the in-house state-of-the-art rendering technology. So having these guys work with us means that we're doing something right, and also allows us some visibility into what is happening in 3D rendering in games. So in this presentation, I'm going to divide the presentation roughly into two parts. I'm going to start with sharing some of the insights that we've gained working with the partners about what will the next generation of games look like. Going to dive into some of the challenges that the studios are facing and will face moving into next generation games. Then I'll get to the actual meat of the presentation, talk about occlusion culling. We'll review some of the past algorithms and mechanisms used for occlusion culling, and then I'll present the Umbra 3 occlusion culling system and show how our technology addresses some of these challenges that the studios are facing. And finally, we're going to have a look at some uses of occlusion culling beyond simple rendering optimization in 3D graphics. So the next generation of video games, next generation here is used quite loosely. The next generation obviously is whatever games are being produced right now. Games are constantly being published. There's no real next generation as such, but there's some common themes that many of the studios that we work with have in their current production. It seems to be a time when a lot of the studios are investing into new technology, both in rendering and other aspects of the game engine. Part of it has to do with advances in hardware. There's the current generation of consoles is already over 5 years old, so it doesn't take a genius to guess that there's new hardware, gaming hardware will be coming up. But also there's some common themes with the changes of attitudes that people have towards gaming, brought on by more casual types of gaming and online experiences and mobile gaming that do have influence over how the AAA studios do their work as well. So as with every generation of 3D games, the demand for more visually compelling content is ever increasing. But I believe there are some unique themes and trends in what is currently being produced. There's been a trend towards higher and higher resolutions, obviously, that allow us to get rid of some of the artifacts in rendering. Also, we have now stereoscopic output, etc. But I believe from now on, what we're going to see is focus on the increase in the amount of geometry complexity, which means that there will be more geometric detail in the games to come. And also, the way the geometry is being built, it's no longer okay to come up with a lot of instanced trees or come up with terrain that's constructed from solid geometry. The push is towards artist-modeled pieces of the scene that are just being put together from arbitrary polygon soups to form game levels. Obviously, there's trend for unique texturing, massive texture atlases, so on. There's also sort of a related theme to create worlds that feel more alive than what we see in games of today. That is being done by adding more interactive, more animated, and more dynamic content. Some other themes that we see in the next generation of games, and this in particular is very brought on by more casual type of gaming. A lot of the studios push to reduce load times, meaning not only loading of the initial game launch, but also minimizing loading in transitions between parts of the scenes, and preferably getting rid of any kind of transition waiting altogether to create worlds that are just seamlessly connected. You just move on in an open world. And this trend, started by Grand Theft Auto and the likes. And there's the screen capture here is actually from a relatively good example of that, but something completely different. It's from Minecraft. This is Lannisport from Game of Thrones, built by someone in Minecraft, painstakingly, I'm sure. And that also takes us to more dynamic worlds. That is obviously like only dynamic. There's nothing static about Minecraft worlds, but AAA titles, a way to make the game scenes more realistic is to allow users to interact with the environment and have the environment react in a dynamic fashion. Another theme is the plethora of gaming platforms around there that game studios need to address. There's obviously the current generation of consoles that's not going anywhere. Anyone producing a game right now will have to target the current generation as well. There's the next generation that hasn't been publicly announced yet, but we know is around the corner. And then PC gaming isn't going anywhere. And even on PC, the fragmentation now seems to be increasing. There's seems to be quite a push towards like Linux gaming quite recently. Just a couple of days ago, Gabe Newell from Valve announced that the Source engine has been ported to Linux, and it actually runs faster than Windows. And then also mobile gaming. I mean, it's been so far mobile gaming has been treated as completely separate. Like the games are targeted for mobile only; they're much simpler. But we've seen some of the engines being ported onto the mobile device and run at least some fairly convincing demos. And that trend, I'm sure, is going to continue. So let's look at some of the challenges that the studios and our clients are facing in building their next generation games. Complex scenes. Adding more visually compelling content means making the scenes more complicated. this is a photograph, but it's there to show what could be, basically. You can see quite a bit of dynamic action going on there. Lots of things moving, if you can extrapolate from here. And lots of geometric detail. Buildings that fetch from different textures, it seems. Pretty realistic looking lighting, so on. So what does that mean for game studios in the game production? Well, for one, artists will have more work at their hands. If it's not the programmer that will construct terrain from random data, it will be the artist actually modeling every single piece of the 3D scene. And it's not only modeling the initial version of the models. There's work involved in creating LOD versions of them, and then also there's all kinds of other work that artists currently do in level design. You have to create connectivity information in the scene for path finding. You need to group objects for optimal rendering, and all kinds of stuff like that. And it's arguable that in the future, many of those things cannot be done manually, but automated mechanisms need to be put in place. And what we hear from these partners a lot is that almost everything else in game production can be sacrificed for rapid content iteration. It's when you have a team of artists building up a world together, and somewhere they need to put their creations together and then run that in the actual game runtime to see whether it actually flies. And it's ever so easy to minor modeling mistakes that result in bad experience for the user. So these architects that are building the 3D worlds, what they need is to be able to see what they did immediately in the running game engine. Another thing, obviously, with more geometric complexity, the amount of data that needs to be rendered will increase. Rendering performance is always an issue. Even with the newer hardware, there will just be more work for the rendering pipeline to do to fill it up. And also, like performance of the other engine subsystems will be affected by more complicated scene topology and geometry. Things like AI audio and physics and other simulations in the engine need to work in relation to the surrounding geometry. And if there's more of the surrounding geometry, there's more work to do. And also, obviously, there's going to be more resources to manage in the game engine, the game runtime, and both loading times and the use of memory in the game engine are a constant concern. Another challenge will be caused by the added level of dynamic elements in the scene. Game engines today can cope with a limited amount of dynamic objects, and engines will need to be updated for more dynamic nature of scenes. So it's part of dynamics in the scenes is just for like visual wow effects, but also increasingly we're seeing dynamic changes actually affecting the gameplay logic. Things like walls breaking and doors opening, tunnels collapsing, and also like users actually generating content, building and destroying stuff in game worlds. So in the quest towards photorealistic output, lighting and shadows will obviously play an important role. Indirect lighting is still mostly done as a pre-process. There's approximations in real time that can be used, ambient occlusion and so on, and the push is definitely towards moving most of this into the game runtime to support dynamic movers, dynamic light sources, dynamic shadow casters, dynamic receivers, and so on. The number of light sources will need to increase if we want to get to photorealistic results, and complicated lighting setups with like reflections and stuff like that in scenes will be more prevalent. Then obviously one challenge is going to be studios that target multiple platforms need to have a way of efficiently utilizing the hardware resources for each of these platforms, but still be able to leverage the work that they do on one platform to the other. The future hardware, the trend is towards more cores on your CPU or GPU, from 8 that we have now into the thousands on GPU. So game engines today are multi-threaded or task-based, and that creates, with like synchronization issues between the cores and between CPU and GPU, make building a game engine that performs well that much more difficult. Scalability is one aspect. People want to utilize the same technology, the same content from low end to high end, and solutions that provide means of addressing this and also abstracting away the running platform will be of high demand. So let's have a look at one way of addressing some of these challenges. That is occlusion culling, and that is what we do at Umbra. So occlusion culling, if you're not familiar with the term, basically means concentrating on the objects that are visible. Seems simple if you never thought about the problem. You only see visible objects, so why should you spend any effort in things that are not visible? Well, it turns out it might be more work to figure out what's visible in advance than compared to just rendering everything and letting the GPU depth buffer take care of correct visual results. But you can probably, in this image, you can see the potential benefit that occlusion culling could give you. On the left, it's a city scene seen from above, where if we don't do any sort of occlusion culling, any visibility-based optimization, that's what we have to process, all of those buildings there. Whereas in reality, those are the buildings that we see in the camera view. So it's basically simple as that. Save cycles by not processing things that are not visible, so that you have more cycles to use for the elements that are visible, and that you can use those cycles to make them more visually appealing. So some of the requirements for an occlusion culling system in general, and then specifically in relation to the changes to the not the shift, but sort of like gradual change to more compelling visuals. The first one is that the culling system preferably should produce correct results, which means that it should never say that something is not visible when some part of it actually is visible. Seems simple. Again, there's lots of games shipped out there where if you're smart, you can spot artifacts where things are popping in and popping out. Output sensitivity means that whatever algorithm you employ for occlusion culling, preferably when you increase the number of objects that are not visible, the amount of time you spend in doing occlusion culling should not increase. Preferably, we don't want the artist to know anything about this, that there's occlusion culling going on. The only way that the artist knows about it is that the game runs faster, period. We do need to be able to support visibility relations between things that are static and things that are moving. we do need to be able to adapt to changes. If there's dynamic changes in the 3D world, if buildings collapse, that changes visibility, obviously. You can now see through where you previously couldn't. So that we need to be able to support that. We do need to support massive scenes. One of the trends with these reducing loading times and getting rid of transition volumes is that you end up with basically massive scenes, and your occlusion culling system should not restrict you from building massive worlds. Another aspect is with the going forward to photorealism, where there's going to be more lights, more shadow casters, and in some of the games, it is actually the case that more time, the GPU spends more time processing the lights, building shadow maps, etc., than it spends time in actually producing the final image that you see. So, preferably the same mechanism could be used to optimize the generation of shadow maps and such. And then some more technically oriented requirements. It'd be nice if the occlusion culling itself as well could take use of the hardware resource available, meaning that you can run it on multiple cores, and it should not require specific hardware or platform. Like, you want a system that works across the platforms that you develop for. So some of the ways that occlusion culling has been done in the past. So we start off with doing just view frustum culling. So shouldn't really be on this list, since that's not doing occlusion culling basically. But it's sort of like in considering your alternatives, you should still always consider that. Like, there are games where just no point in doing occlusion culling, like a soccer game where you always see everything. Like, you're not going to get any wins from doing occlusion culling. The GPU helps you doing visibility determination. The modern GPUs have a feature called occlusion queries, where you can basically, after the fact, after you render something, you can ask what were the objects that were visible. So that gets you really accurate visibility results. Used as trivially as I just described, that has the downside that it's too late. Like, you already rendered everything. So what you do then is that you render everything twice. Once with in a cheaper fashion to optimize the second stage, where you render really expensive stuff, but only the visible things. Or then you use old results. Use results from a previous frame or the frame before that, and that's where you get into issues with non-conservative results. Another traditional method of doing occlusion culling is PVS systems, potentially visible sets, where basically you establish the visibility relations for your scene in advance. So that only works for static things, obviously. Like, you determine visibility relations without knowing where the dynamic things are going to be. So the upside of that is it's really fast then in runtime to query the visibility information. But it's a pretty hard trade-off between how much memory you're willing to spend for saving your PVS matrix. It's basically like n squared. It's like volumes in your scene times the objects in your scene. And as you grow larger and larger worlds, like that's going to become unbearable. You can always trade off by doing less accurate culling, but then you get to a point where it may not make any sense to use occlusion culling at all anymore. And also, it's a heavy pre-process. So we just established that we want the artist not to have to wait for anything in getting run the game. So we don't want to impose like that hour-long pre-process. Then into maybe like more modern approaches to occlusion culling. Gorilla, for example, in their Killzone franchise, they have a very nifty method of doing occlusion culling on the PS3, doing software rasterization on the SPUs on the PS3. So you basically, you do what the GPU would do, but you do that on the CPU, and you do a simplified version of that. So to be able to do a simplified version, you need simplified geometry. So basically what happens is that the artists create simplified versions of your models, and then you render those to create a view of visibility in your scene. So that's not good either, right? It's now the artist has to create simplified versions, and on top of that, it's not very easy, because you want your simplified models to be simplified in a fashion that that they still are a conservative approximation of the occlusion of the original model. So if in simplifying a model, you happen to remove a hole that was in the original model, then you're going to get wrong results using that simplified model. Then finally, we have portal systems. So a cells and portals system is basically that you have a topological database of your scene, where traditionally it has been manually created. So you have artists that place portals in places that seem like good places for portals, so like doorways and so on. And then you collect the objects in each of the cells, which could be like rooms or something, and then you just determine like which of the cells are visible and process the objects in those cells. So that's pretty nice, and it worked well if it's like if it's as I described, like an indoor environment with doors and rooms, and where the artist can clearly see like what is a good position for a portal. But as we move into like open worlds where there's like indoors and outdoors environments and complicated topology in like all 3 dimensions, it's not only it's difficult for the artist to know what would be a good place for portals, but also it could mean that the amount of portals need to increase quite dramatically. So the amount of work involved in placing those portals is going to jump up. But still, so the portal system in runtime, it's got a lot of useful features. It gives you pretty accurate occlusion. It's output sensitive. You only process the objects that are in the cells that you traverse. Pretty low memory usage, and you can scale that like by scaling the amount of portals. And you can do that all on CPU. So at Umbra, we've implemented occlusion culling solutions utilizing all of these methods that I described. For the next generation, we've sort of armed with these tools. We've come up with a new way of doing occlusion culling that takes the best parts of these methods that I just described. So what we do is we create a simplified version of the scene topology, which is exactly the portals and cells graph, but we do that automatically. Then, when doing that automatically and being able to support all kinds of scenes, outdoors and indoors and whatnot, means that there could be quite a few portals in what we produce. So another aspect of the product then is we need to be able to deal with massive amounts of portals in runtime. And what we do there is we pick software rasterization as another method, and we software rasterize the portal graph. So that we can process the portals really fast and then do tests against the generated depth buffer after the fact. So here's a view of the Umbra 3 pipeline. We have no restriction on the type of geometry that we take as input. It's arbitrary polygons. We run a pre-process that is relatively fast and can be done localized, like we don't have to have global information of the scene. So basically we take a group of objects, pre-process those objects, and build a portal graph out of them. Then in runtime we take these pre-processed chunks of data, slam them together, and traverse the graph, doing the software rasterization, and give you the visible objects. So let's dive a bit deeper into how do we automatically generate portals and cell graph. So what we do is we transform the problem from the continuous domain into a discrete domain. So in other words, we voxelize the scene. So the picture here shows a voxelized version of that object there. Armed with the voxelization, we look at the empty voxels, we look at the empty areas, and start putting together empty voxels to build things that are well connected. And then with these well-connected empty regions, we hook them up to each other by spanning portals in between them. So here's a view of one scene that where we have the voxelization of the solid geometry of that scene overlaid on top as these cubes. So you can imagine that's the way we analyze the scene. We split it up into voxels and then start processing the empty space in that scene. And what we end up with is something that looks like this. Here you have rectangles or quads that are portals, and you have the cells that join the portals together. In runtime then, we use this simplified version of the scene that we have. And we traverse the connectivity, the spatial connectivity information, generating a depth buffer as we go. And so this rasterization, the sort of mind-bending aspect of it is that we're not actually rasterizing geometry. We're not rasterizing the occluders themselves, even though the end result looks like it has occluders rasterized. So we do the opposite. We rasterize the portals, the things that are non-occluders. And doing that allows us to get conservative results. It allows us to make the rasterization process much easier because we can safely basically round up. We don't need to deal with difficult gaps between polygons or anything like that. We can make the process really fast, still getting a result that fairly accurately represents the important occlusion properties of the scene. That's what's demonstrated here. There's a depth buffer view of the scene in the middle that has been produced by the GPU, and here's our depth buffer as seen by Umbra. So you can see a lot of detail is missing, but the important things in terms of being occluders are still there, like the buildings and the ground and so on. And obviously, it's possible to scale between more accurate results, trading off the amount of data that needs to be produced. So let's go back into the requirements that an occlusion culling system has. The fact that we turn the scene into a voxel representation means that we get conservatively correct data. We make the problem that much more simpler, that we can guarantee that the results are conservatively correct. Like we never underestimate an occluder, basically, with this representation of the scene. And we can get to similar accuracy to the software rasterizers that use hand-simplified models, basically. So from the voxel representation, we could use that for occlusion culling as such, but it's ridiculous amounts of data. So what we need to do is come up with something that captures the visibility relation information of that voxel representation in less amount of data, and so on. That's the cells and portals graph that we then build from the voxels. That also means that the amount of memory that we use for occlusion data is independent of scene complexity. Doesn't matter how many more polygons you add, our data is going to be the same size, or it's only going to be capturing the occlusion property. And obviously, big part of the product is that we can do this automatically, that the artist doesn't need to be involved, doesn't need to know about it. Dynamic objects can be supported both for determining the visibility of them and using them as occluders via the use of the software depth buffer for doing the final occlusion testing. So we can augment the depth buffer with dynamic objects by just rasterizing them, the objects themselves there. And also we can test dynamic objects or hierarchies of dynamic objects against the depth buffer that we produce. Another nice property is that we can support massive worlds without affecting content iteration times by being able to do local pre-processing and then using a collection of locally pre-processed data in runtime. So that allows you to stream parts of the occlusion data, and it allows you to only have to recompute a small part when you do a change to the scene. The data that we access in runtime is read-only. There's no runtime modifications for the data. So that allows for being able to process the data in parallel. There's no write locks that need to be taken. And the same technology can be used for culling light sources, culling shadow casters. And depending on how the game engine does lighting, this can be done in parallel with doing the main view occlusion culling. And it's doesn't use any exotic hardware. It's simple software library written in C and works across the board on all of the gaming platforms, from low-end mobile to high-end PCs and consoles. And it's actually usable on the range of these devices as well, since you can scale the accuracy of the results depending on the amount of processing power and the amount of memory you're willing to sacrifice. So I will show you a video of Umbra occlusion culling in action. So you see the camera view rendered here on the left. In the corner here, you see the occlusion buffer, which is the thing that is produced from traversing the polar graph and represents the important occlusion features of the scene. And on the right here, we're trying to visualize the part of the frustum that actually needs to be that is visible at any moment in time. So the larger frustum there is the original frustum, and the green volume there represents what is visible. So you can probably see that a lot of the small props are nowhere to be seen in our view of the world, because they're not important occluders as determined by the algorithm. And that means that we have less data to store and we have less nodes in the graph that we need to traverse in runtime. So another quick clip on, just a second, sorry. So this is a visualization on the creation of the view cells in our graph. The black thing here is solid geometry, and everything else is empty space. So what you see happening here is okay, here we go. To get you some idea of what a cells and portals graph would look like that we produce. So, analyzing the empty space, we end up with this division into cells and the portals between them. A couple of words of what we think the data that we build from the scene can be used for beyond rendering optimization, and that we're actually currently developing with partners uses for this data for. So one of the things that also needs the same kind of like visibility relation information and topological connectivity information is audio for realistic sounding 3D audio. But also the same spatial connectivity information can be used for just game logic, for AI, etc. For some reason, the image here isn't showing. In any case, thank you for listening. Go and enjoy Assembly 2012. If this tickled your interest, there's more info on umbra3.com, and there's open positions on that website as well. Here we go. Thank you very much. I'm going to be here for questions, discussions, so please don't hesitate to move forward to ask questions.